Now in its 27th year, the school year 2024 to 2025, the Philippine Mathematical Olympiad is the oldest and most reputable nationwide mathematics competition among high school students. After its trial run in 1984, it was officially launched in 1986 and has been held annually since 2007. The country's contestants to the International Mathematical Olympiad are chosen from the top students who compete in the Philippine Mathematical Olympiad. The PMO is a project of the Mathematical Society of the Philippines and the Department of Science and Technology Science Education Institute.
Hello and welcome to another entry of the PMO video series. My name is Immanuel Balete and today we'll be talking about the infinite geometric series. What is a geometric sequence? A geometric sequence is a sequence of numbers which can be defined with two values, which are a and r. A and r. So a is what we call the first term. As you can see here, a is the first term, and r is what we call the common ratio. So we call it the common ratio because if you look at this sequence, for any two consecutive numbers, for example, for any two consecutive numbers in this sequence, the ratio is going to be equal to r. So another way of thinking about the geometric sequence is you have a first term, and for every succeeding term, you multiply the common ratio. So from a, you multiply r to get ar, then you get ar squared, and so on. Here are some examples of geometric sequences. So, for example, in the first sequence here, a is equal to 1 and r is equal to 2 because you multiply by 2 to get the next term. Another example, the constant sequence is also geometric. So this one has a first term of 10 and your common ratio is 1 because the ratio between any two consecutive terms is 1. Similarly, you can solve that this third sequence is also geometric with a first term of 27 and a common ratio of 45 over 27 or 5/3. So this one is, this time the common ratio isn't an integer, which is perfectly fine. It's still a geometric sequence. And finally, our fourth sequence has negative numbers. So the first term is -7 and your common ratio is -2. So these are all examples of geometric sequences. Now, what are some sequences that are not geometric? These are non-geometric sequences. The first one here is actually an arithmetic sequence, 1, 2, 3, 4, 5. It's not geometric because if you look at the ratio of consecutive terms, so 2 over 1, 3 over 2, and so on, you'll see that these values are not equal to each other. So there's no common ratio, and thus it's not geometric. Similarly, this second sequence here, which you might recognize as the factorial sequence, um, the ratio between consecutive numbers is also not constant, even though there is a pattern. So it's 2, 3, 4, and 5. But because it's not constant, there's no common ratio. And so this does not constitute a geometric sequence either. Now, what we'll mainly be focusing on is the geometric series. And when we talk about a series, we are adding up the terms in the sequence. We want to know how to evaluate this sum, a plus ar and so on until a times r raised to n minus 1. And the way that we usually derive the formula for this is to set this sum to a variable s and then multiply both sides of the equation by r. So a will become ar becomes ar squared, and so on until the last term. And you can clearly see why this is helpful because all of the middle terms will appear in both equations, which means when we subtract, they'll all get canceled out, leaving you with a minus ar raised to n. Take note that we need to switch the sign since we're subtracting the second equation. Now from there, you can isolate s and you get this expression, a times 1 minus r raised to n divided by 1 minus r. One note, one thing, or one detail you might want to clarify is what happens when r is equal to 1. Clearly, something wrong happens with the formula when r is equal to 1. So you might want to recheck in the original geometric series what exactly happens when r is equal to 1 and how come this formula doesn't work anymore. Here are the sequences from the previous slide. So you can try out using the geometric series formula for each of these sequences. All you have to do is identify the first term. So for example, in this first series, a is equal to 1, r is equal to 2. And we have a new variable n now that we need to find. N is the number of terms. This n refers to the number of terms. So for example, 1 plus 2 plus 4 until 2048, you can verify n is equal to 12. And then to find the sum, we just substitute s is equal to a times 1 minus r raised to n all over 1 minus r. Sometimes you might want to switch r and 1. So you might rewrite it like this to avoid negative numbers. So you can also rewrite it like that. And this evaluates to 4095, which you can verify is correct using a calculator. So for the other three series, rather, you can try out using the formula and verify it using a calculator. Now here is the main topic that we really want to talk about, which is the infinite geometric series. When we say infinite geometric series, we're not talking about an infinite sum, not necessarily infinite sum, but we're talking about a series with infinitely many terms. So what happens when you take this finite formula, but we're going to extend it to have infinitely many terms. So this would go on forever. And essentially, we want to know what happens when n approaches infinity. You might think that that automatically means the sum will be infinite, but this is not always the case. For instance, if we let r be 1/3 and we let n be a very large number, say 10 raised to 100, a Google, then notice that r raised to n becomes 1 over 3 raised to 10 raised to 100, or 1 over some very, very big number. And this number is 1 over some huge number is going to be approximately 0. Which means in the formula, in our original formula, a times 1 minus r raised to n over 1 minus r becomes approximately a times 1 minus 0 over 1 minus r, or a over 1 minus r. And because we're taking an infinite series, so n gets bigger and bigger. As we make n even bigger, this the value of the sum will get closer and closer and closer to this, because r raised to n will get closer and closer to 0. So it seems for certain values of r, we actually get this new formula of a over 1 minus r. And in fact, you will discover that as long as the absolute value of r is less than 1, or in other words, r is between -1 and 1. If r is strictly between -1 and 1, then we can actually define the infinite geometric series a plus ar and so on to be equal to a over 1 minus r. So this definition works because, again, as you make n bigger and bigger, the sum will get closer and closer to to a over 1 minus r. So this is essentially the important formula to remember when working with an infinite geometric series. And here are some examples where we can try it out. In the first series we have here, a, the first term is 2, r is equal to 1/2. And note that r is indeed between -1 and 1. So we can apply the formula. So the sum will be equal to a, oops, wait, bad color. Let's put it over here. This will be equal to a over 1 minus r, which evaluates to 4. So this sum is actually equal to 4. And you can check if you use your calculator and add up the first few terms, you'll notice that it gets nearer and nearer to 4. So when you do it infinitely, then we can define it to be equal to 4. And if we try with the other sequence here, so 2 minus 1 plus 1 half and so on, this time your first term is 2, it's still 2, but your common ratio is -1/2. So 1 minus, take note of the sign, -1/2. And if you evaluate, this will be equal to 4 over 3, which makes sense because it's smaller than the other sum because you're subtracting every other term instead of adding it. So this makes sense. You have got sum of 4/3. All right, now let's try to use what we've learned about the infinite geometric series to solve some problems from the PMO. First, we have the 19th PMO, a problem from the 19th PMO. An infinite geometric series has first term 7 and sum between 8 and 9 inclusive. Find the sum of the smallest and largest possible values of its common ratio. So I encourage you to pause the video here, try it out on your own first, then continue once you're ready to hear the solution. All right, so whenever we work with an infinite or even a finite geometric series, the most important thing is to identify what your first term is and what your common ratio is. We're given already in the question that the first term is 7, and we don't know what the common ratio is, so we'll just let it be equal to r. So we're told that the infinite geometric series has a sum between 8 and 9, but we know by the formula that this sum is a over 1 minus r, or 7 over 1 minus r. So we are told that 7 over 1 minus r is between 8 and 9. And we want to know the range of values of r. So we simply solve this inequality for r. We can split this into two inequalities. Or if you want, you can also do them together at the same time. So first we have 8 less than or equal to 7 over 1 minus r. We multiply both sides by 1 minus r. And when we do this, we need to be careful. We need to make sure that we check the sign of what we're multiplying by. So because otherwise, if 1 minus r is negative, we need to flip this sign. So do we know for sure that 1 minus r is positive? And in fact, we do, because the fact that the geometric series has a finite sum tells us that this r must have an absolute value less than 1. So we know for sure that 1 minus r will be positive, which means we can safely multiply both sides of the inequality by 1 minus r. So solving this, you have 8 minus 8r less than or equal to 7, or rearranging, you will get r is greater than or equal to 8. Okay, now let's do the other side. 7 over 1 minus r is less than or equal to 9. Again, we know that 1 minus r is positive, so we can multiply both sides by 1 minus r without changing the inequality sign. Simplify this and rearrange, and we will get r is less than or equal to 2 over 9. So we conclude from both of those that r must be between 1/8 and 2/9. And to double check, this makes sense because 1/8 is indeed smaller than 2 over 9. So our inequality makes sense. And our final answer, since we want the sum of the smallest and largest possible values, so we take their sum and we get 25 over 72. So the answer for this item is letter D. All right, next. We have one more item, this time from the 17th PMO. An infinite geometric series has sum 2014. If the sum of their squares is also 2014, find the first term. So again, pause the video and try this problem on your own first, then come back when you're ready to hear the solution. Okay, so we've got an interesting geometric series here. Counterintuitively, even if you take the sum of the squares, it seems that the sum doesn't change. So you can see you can get some weird things happening when you work with infinite numbers. Uh, Again, we need to identify our first term and common ratio, but we don't know any of them. So we'll just leave it as A and R. The first, the original geometric series, so that's A plus AR and so on. We know that this is A over 1 minus R, and we are told that this is equal to 2014. Now we need to get the sum of their squares. So that's A squared plus A squared R squared, and so on. Now what do we do with this one? We observe that this is also a geometric series. This time your first term is A squared, and your common ratio is R squared. So you're just multiplying by R squared every time, which means we can again apply the infinite geometric series formula. So we have A squared over 1 minus R squared is also equal to 2014. And now you have two equations in two variables, which means you can solve for A and R. So now it's just a bit of algebra. Okay, well, you could observe that A squared over 1 minus R squared can be factored as A over 1 minus R times A over 1 plus R. Substitute what we know. So you have 2014 equals 2014 times A over 1 plus R, or which means A over 1 plus R is equal to 1. So now let's try using this equation and this equation since they look relatively simple. A over 1 minus R is 2014 and A over 1 plus R is equal to 1. Since we want to solve for, you can solve for A and R from here, but just to make it faster, we'll try to eliminate R. So let's take the reciprocals. And then we can add these two equations together to get 2 over A equals 2015 over 2014. So solving for A, you get 4028 over 2015. And this is the first term, so our answer is letter D. And if you want, for completeness, you can also solve for the common ratio, which will be equal to 2013 over 2015. Yes. So that's it for the infinite geometric series. I hope you learned a lot and see you in another video. Thank you.